Okay, let's move on and talk about the concept of formula mass. And if you understood molar mass, so the mass of a molecule, an entire molecule in grams per mole, well, I got good news. You're going to understand formula mass because formula mass is akin or the same concept as molar mass. However, it's the mass of the formula unit of an ionic compound. Now, if you're like, what the heck's a formula unit? Well, this is something that was covered in nomenclature. And when we look at molecules, right, if we have water, that exists as a distinct molecule. If we have a molecule like carbon dioxide, that exists as a distinct molecule. If we have a molecule like ammonia, that exists as a distinct molecule. Now, what do these all have in common? They're all made from nonmetals. So those are molecules. They exist as individual discrete units. However, ionic compounds that are made from a metal and a nonmetal, and now the example they're using here is sodium chloride. Sodium is a metal, chlorine is a nonmetal. When we have a formula, or sorry, an ionic compounds don't exist as discrete individual molecules. You don't find a molecule of sodium chloride. That's incorrect. You don't say there's a molecule of sodium chloride. There's no such thing. Okay? Why? Because ionic compounds exist in crystalline lattices, like the one that's shown here, right? We have our chloride, then a sodium, then a chloride, then a sodium, then a chloride, then a sodium. And so the formula mass is like an empirical formula, right? If I look at all this, there's many sodium atoms and there's many chloride ions. But if you break it down, the simplest whole number ratio of them is 1 to 1. And so the formula unit of sodium chloride is NaCl. And therefore, its formula mass is just going to be simply adding up the mass of one sodium and one chlorine to give you, in this case, 58.44 AMU. So that means the molar mass of 1 mole of sodium chloride, so that means 1 mole of sodium atoms plus 1 mole of chlorine atoms. If I add that all together, I get 58.44 grams. Okay? So again, if you're like, this looks exactly like what you did before, yeah, but now we're talking about ionic compounds. Okay? So that's why it's so important to understand the nomenclature of molecular compounds, so covalent compounds, and ionic compounds. I'm going to skip the part about mass spectrometry. You can read that if you want. I'm not going to ask you anything about that. And let's talk about what's called percent composition. Now, if you have $1 and you have, 2 dimes and you have the rest in nickels, let's say, you'd say it's 20% dimes, right? And you say it's 80% nickels, right? Let's say you had $1, but you had 2 quarters and 5 dimes. You'd say it's, even though there's 2 of one and there's 5 of the other, you'd say it's 50-50, right? It's 50% quarters and it's 50% dimes. And that's the same kind of concept that we see with percent composition of an element in a compound. Why? Because just like quarters and dimes and nickels have different values, right? Elements have different masses. Okay. So let's say we were talking about, it says here N is the number of moles of the element in 1 mole of a compound. And the percent composition is this formula here. So we take the number of moles of that element, okay, and we get that from taking the molar mass, okay, um, multiplying it by the number of moles of the element in 1 mole of the compound and dividing it by the total molar mass of the compound, or the molar mass of the whole compound. Now, I kind of bargled my words there. It's a lot easier to explain if we look at the example here. So this molecule here that's shown here, this is ethanol. So this is ethanol, and if you're like the same ethanol that's in alcoholic beverages, absolutely, okay? It's also used as an additive in gasoline. So this is CH3, CH2, and then you have an oxygen here. I guess I should use a different color. Oxygen, and then a hydrogen here. So that's ethanol, and there's the formula, the molecular formula for ethanol. And so if you tally up the mass, and I'm not going to do that right now, but if you tally up the mass of 2 carbons plus 6 hydrogens plus 1 oxygen, you're going to end up with a mass of, and you can see it here in all these denominators, of 46.07 grams per mole. Now, we've already learned how to do that, so I'm not going to repeat it. But if I want to know the percent by mass of carbon, Well, I can see that there's 2 carbon atoms in the molecule. Well, how much do they make up overall with respect to the percent of mass? Well, if each carbon weighs 12.1 grams, 12.01 grams rather, I'm going to take 2 times that since there's 2 of them, and I'm going to divide that by the total mass. And I get that by mass, the ethanol molecule is actually around 52% carbon. Now, there are more hydrogen atoms. Yes, there's a lot more, right? There's only 2 carbons, but there's 6. There's six hydrogens, 3 times as many. But what's the difference? Hydrogen is a lot smaller, right? It doesn't weigh nearly as much. So the percent of hydrogen, even though there's more hydrogen atoms, they are so much lighter. They're 12 times lighter than a carbon. So even though there's more of them, if I take 6 times the molar mass of a hydrogen, I get that hydrogen only makes up about 13%. Okay, oxygen weighs more than a carbon. It weighs 16 grams per mole, but there's only 1 oxygen. And so we take 16 divided by the total mass, and we end up with 34.73. So if I asked you to calculate the percent composition of a bunch of different elements in a compound, what should the total of their percentages equal? It should equal 100%. So that's an easy way to check to make sure you would have a problem where I asked you to calculate percent composition correctly. Well, with those concepts in mind, let's take a look at a problem here. It says phosphoric acid, which is not a strong acid. Phosphoric acid is actually a weak acid, is a colorless, syrupy liquid used in detergents, fertilizers, toothpaste, and in carbonated beverages for a tangy flavor. Calculate the percent composition by mass of hydrogen, phosphorus, and oxygen in this compound. The first thing I want to do is I want to determine the molar mass of phosphoric acid. So I'm going to figure out the molar mass of, H3PO4. Let me do it a little bit quickly here. We've got hydrogen. We've got 3 times 1.01, so 1.01 grams. So that gives me 3.03 grams. And this is in 1 mole. I could put grams per mole. Maybe I should, just to be clear. So grams per mole. That gives me 3.03 grams per mole. If I calculate the mass of my my phosphorus, I've got 1 times 30.97 grams per mole. And that gives me 30.97 grams per mole. And then for my oxygens, I have 4 times 16.00 grams per mole, and that equals 64.00 grams per mole. And I tally all that up. I got 98.00 grams per mole. Now, once you've mastered the concept of calculating molar mass, I can tell you a much faster way to do this when you're practicing. You take your internet browser and you type in phosphoric acid molar mass, or you type in H3PO4 molar mass, and trust me, it will come up immediately on Google and it will be accurate, okay? Now, obviously, you're not going to have that on your exam because you're using Respondus, but it's just a quick way to do it. Now, if we want the percent by mass of all these, I've already calculated the total mass of each atom, so it kind of speeds things up. So if we want the percent of hydrogen, it equals the total mass of hydrogen, which is 3.03 grams per mole, divided by the total mass, which is 98.00 grams per mole, multiplied by 100%. You can see that the units of grams per mole cancel, and I'm left with 3.09 is what I'm reading. So 3.09%, like that. Let's do the same thing for the phosphorus. So my percent of phosphorus is going to be equal to 30.97 grams per mole divided by 98.00 grams per mole multiplied by 100%. Same old calculation over and over here that you're going to see me repeat. I get 31.60%. And then finally, for my percent of oxygen, and you can see that it must be mostly oxygen by percent composition. So we have 64 divided by 98.00 grams per mole multiplied by 100%. And grams per mole cancels. I punch all that spinach into my calculator and I end up with 65.31%. So when I tally up when I tally up 3.09, the 31.60 and 65.30, it should equal 100.00. Now I might have made a mistake, 3.09, or even if you're off by, you know, a hundredth or something, that your answer is still right. 61.31. Yeah, it's perfect. So you tally all three of these up, and you end up with 100% left over, or that's what it equals. So that's a good check. You know that you've calculated percent composition correctly. Now, if you're wondering, when would I use percent composition in real life? Well, if you think about analytical chemists, if you watch those crime shows, like, I don't know, what are they called? They're probably old now. What was the crime show? Shoot. NCI, what's that? Anyhow, I can't, it escapes me right now, but there used to be some CSI. Yes, thank you. Thank you. CSI. That was a big crime show for a while, right? And if you think about what you saw in those kind of shows, and maybe you never watched them, but what you see them do routinely is they would analyze someone's blood, and they'd say, oh, look, there was cocaine or heroin, in this person's blood. Well, how do they know that? There's nothing that you can't just put it in an instrument and then the instrument tells you it's cocaine. It's going to give you maybe a molar mass and the percent composition. And so, since cocaine always has the same percent composition of carbon, nitrogen, oxygen, hydrogen, right? They're able to determine, or at least narrow it down. Anyhow, and then they have other ways to be absolutely sure. But that's a legitimate answer to, when would percent composition would be important. It's really important in identifying, unknowns and maybe metabolites, things like that. All right. Well, let's talk about empirical formulas. And I don't like the title of this slide a whole lot. I changed it a little bit it's more like how to use percent composition to calculate empirical formulas. That's more what's going on here, right? Because we just talked about how to evaluate mass percent. Now, if we assume if we take that mass percent and we convert that into a mass and we assume that that's the amount of mass in 100 grams of substance, we can figure out the number of moles, right? Then if we compare the number of moles of each element in a compound, we should be able to come up with, a simple whole number ratio of those elements. And from that, we can determine an empirical formula. Now, we might not be able to get a molecular formula, and I'll give you a clue. If I ever ask you to calculate or to determine a molecular formula using this method, I'll always design the question so that you'll be able to do it. I'm not going to leave you hanging out in left field like, oh, this is impossible. No. But the idea is that we should be able to do it. Or any problem, all I'm trying to say is if I ask you to calculate or determine molecular formula, I'll always give you the clues to be able to solve for it. If you're unsure about what I mean, let me show you. Okay, so vitamin C, it's shown over here. So I kind of gave you the answer. If you look at the picture, you could figure it out probably. But anyhow, you all know what vitamin C is. It's ascorbic acid. It's common name in the chemistry world. Ascorbic acid cures scurvy. It's composed of 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. Okay? Determine its empirical formula. Well, let me show you the strategy of how to do this. And once I show you, you'll know it forever. And if you ever run into a problem like this, you'll be able to solve it pretty quickly. There's an assumption that we're going to make here. Now, to some of you, I'm sure it's intuitive. To others, maybe not as much so. But look, if we know that we have this much percent carbon, this much percent hydrogen, and this much percent oxygen, if we were to add up those three numbers that I have circled in blue, what would we get? We'd have 100%. So here's the assumption we're going to make. We're going to assume a 100 gram sample of vitamin C. And if you're not following me, the significance of that would be if I have 100 grams, that means I have 40.92 grams of carbon. That would mean that I have 4.58 grams of hydrogen, and that would mean that I have 54.50 grams of oxygen. Now, if you're wondering what the relevance of those is, remember, when we have a molecular formula, that would be CXHYOZ, like that. Remember that the ratio of these subscripts has to be simple whole numbers. And these numbers, this X, Y, and Z, they're not based on mass, are they? They're based on moles, right? It's a ratio of moles, right? Let me give you another example. What if I had CO2? We know that there is 1 mole of carbon for every 2 moles of oxygen, right? What if I had, I don't know, ammonia? I know that there's 1 mole of nitrogen for every 3 moles of hydrogen. It's got nothing to do with mass. It doesn't mean there's 1 gram of nitrogen and 3 grams of hydrogen. That's insane. Okay, so we always have to break it down to moles. So let's figure out the number of moles of each one of these substances, each one of these elements. First, let's do it for carbon. We'll use the molar mass from the periodic table, 12.01 grams per mole. Okay, and look, grams of carbon cancel, and I'm left over with the number of moles of carbon. I end up with 3.41 moles. Okay, great. But I'm not going to have 3.41 as a subscript, am I? I'm going to show you how to get rid of it, though. Look, let's do the same thing for hydrogen. We know that in 1 mole of hydrogen, we have 1.01 grams of hydrogen. Grams of hydrogen cancel. I'm left over with moles of hydrogen, and I get 4.53 moles, like that. Moles of H, and I should put moles of C up here. We do the same exercise for the oxygen. 1 mole of oxygen has 16.00 grams of oxygen. I multiply all that spinach out, and I get 3.41. So I get 3.41 moles of oxygen. All right, and again, the units of grams cancel. But again, there's no such thing as 3.41, C 3.41, H, what is it, 4.53, O 3.41. That doesn't exist because X, Y, and Z, these subscripts have to be simple whole number ratios. So what's the strategy? If I go back here, it says divide by the smallest number of moles. Let's go over here. The smallest number of moles is the same for 2 of them. So we're going to divide all of these by 3.41. You're going to forgive me. I'm going to do it over here just to save a little bit of time. Divided by 3.41, divided by 3.41 moles, divided by 3.41 moles. Now it's easy to see what you get for carbon and oxygen. They're present in a 1-to-1 ratio. If I take 4.53 and I divide it by 3.41, I get 1.33, around 1.33. Again, and I'm going through this a little bit slowly, but look, again, there's no such thing as C1, H 1.3301. That doesn't exist. What's the simplest whole number ratio I could get? And again, it doesn't have to be like right down to the 1,000th or anything like that. It's just got to be really close. If I multiplied this whole dang thing here by 3, what would I get? Can you do that in your head? 1.33 times 3, it's 4, right? So then I would get C3H4O3. And that would be the empirical formula of ascorbic acid or vitamin C. Now, if you were Googling this while I was teaching it, you might have looked up the molecular formula of vitamin C. And its actual molecular formula is C6H8O6. So that is the empirical formula, right? If we divide that by 2, its actual molecular formula, we get its simplest possible ratio of whole numbers. Give me a thumbs up if you're like, hey man, once you showed me the assumption that we made there, yeah, I could figure this out. Yeah, you're going to use the same darn strategy every time when you want to determine an empirical formula. And sometimes you might get lucky. Sometimes the empirical formula is the same as the molecular formula. Sometimes it isn't. But again, I repeat myself. If I ever posed the question in such a way that I wanted you to actually determine the molecular formula, I'd always give you the information to do that. Okay, and I have some examples picked out in the problem set.
Can I ask a quick
go for
question real fast? Yeah, where did you get that 3 from? I'm sorry, I must have missed that. That whole number 3 that you multiplied?
Right. So I have I did it mentally. I did it in my head. So look, if I have this ratio, 1, 1.33, and 1, right? I've got this ratio, 1 to 1.33 to 1. Okay, if I multiplied all that by 2, what would I have? I'd have 2, 2, 2.66 to 2. That's not a whole number ratio, right? That's not a whole number ratio. But if I multiply all those numbers by 3, and again, I just did this in my head, you get 3 to 4 to 3, and those are all whole numbers. Does that help?
That does, thank you.
Yeah, so just a little bit of mental acrobatics there. You got to be able to do a little bit of mental math, in general chemistry.
Can I ask one question?
Yeah, go ahead.
Her question. So I was just assuming that you did the 3 because you had 3 different percentages.
No.
Okay, so you can't do that. Okay.
Oh no, it's got nothing to do with that.
Okay,
You're just trying to take these numbers, those 3 numbers, these 3 numbers right here, and give the simplest whole number ratio. Right? I mean, if you were to come up with 1 to 1.33 to 1, I mean, you could multiply it by any number, right? You could say it's, 6 to 8 to 6, but that's not the empirical formula because that's not the simplest whole number ratio, right? You want to come up with the simplest whole number ratio. All right, well, let's move on from there and try another problem. In case you didn't notice, general chemistry is just replete with problem solving. It is the most effective tool for learning this. And this is kind of, I think, one of the last problems we'll look at for a couple of slides, maybe, until we really get into the meat and potatoes of chemical reactions towards the end of this lecture. Anyhow, it says here chalcopyrite, which is CuFeS2, is a principal mineral of copper. Calculate the number of kilograms of copper in 3.71 times 10 to the 3 kilograms of chalcopyrite. Well, this is just another dimensional analysis problem. Look, I'm not, in the interest of time, since we're in a pandemic and some of our lectures are cut short, I'm not going to show you the whole gory details of working out the formula mass of chalcopyrite. It's not the molar mass, it's the formula mass because it's a formula unit, because it's ionic. But anyhow, I'm not going to go ahead and show you how to do all that. I've just gone ahead and calculated it. It's 183.54 grams per mole. Okay, so there's my formula mass. And it's asking us for the number of kilograms of copper in it. There's a number of ways you could do this problem. You could take the percentage of copper in the compound, and then you could just multiply that by 3.71 times 10 to the 3 kilograms. That works. That totally works. But I like to show my students how to do things in dimensional analysis. And if you understood what I just said and you say, hey, Mr. Dan, I'm just going to try it that way, go for it. It'll work. It'll totally work. But let me show you how to set it up using all the bells and whistles of dimensional analysis. I'm going to start with what I know. I've got 3.71 times 10 to the 3 grams of chalcopyrite. I'll just abbreviate it like that, okay? And I guess I should include the units of mass, okay? And I'm going to convert that into grams since my formula mass is in grams per mole. So I know that there's 1,000 grams in 1 kilogram, like that. Okay, there we go. So now I've got it in grams. And I know that in 1 mole of chalcopyrite, there is 183.54 grams of chalcopyrite. Let's stop right there just for a second. And we see that kilograms cancel, grams cancel, and chalcopyrite cancel. So at this point, we're left with the number of moles of chalcopyrite. So now we're going to come up with a ratio for the number of moles of carbon in 1 formula unit of chalcopyrite. Let's look at it. It's CuFeS2. So if this is our formula unit, and this is 1 formula unit inside this this rectangle here, there's only 1 mole of copper, right, in there. So we can use that conversion factor. In 1 mole of chalcopyrite, we have 1 mole of copper. And we know that in 1 mole of copper, we have, and I have to go to my periodic table here, 63.55 grams of copper. And if you stopped here, I mean, there's nothing wrong with stopping at this point. You'd have the mass of copper in grams, but they want it in kilograms. So we have one more conversion to do, and that is in 1,000 grams. I have 1 kilogram, and there you go. That's the whole thing. Now it looks really gaudy. You know, it looks like there's a lot there. So we cancel grams, and we're left over with kilograms of copper. You punch all that spinach into your calculator, and you end up with a big number. It's 1.28 times 10 to the third power kilograms of copper. Now, again, you could do this one using percent by mass. You could say the percent by mass of copper is 63.55 grams of copper divided by 183.54 grams of chalcopyrite. So that's the percent of copper. And then just multiply that. So if you take 63.55 divided by 183.54, and you multiply that by 3.71 times 10 to the third power, you end up with this answer. Now you're like, Mr. Dion, why didn't you do it that way? That's a lot faster. There's nothing wrong with doing it that way. Okay, that's a perfectly legitimate way to do it. So multiply by 3.71 times 10 to the third kilograms, and that would give you your answer. Okay, gives you the correct answer. So maybe I'll just put answer. Now, again, I'm repeating myself, but look, if you want to do it that way and you understand it, by all means. And if you're wondering, you know, Mr. Dion, why aren't you just teaching it that way? The reason why is what I've found, and I've taught chemistry for a long time. I've seen a lot of students. What I found is that students who, you know, really don't find it that difficult, they will probably solve it using the percent by composition, and there's nothing wrong with that. However, if I have a student who maybe is finding it a little more complex, I find that it's actually easier to start with dimensional analysis this way and just solve it kind of slowly, step by step by step by step. The reason why is because if you start with dimensional analysis, you can always kind of go just one conversion factor at a time, one after another and after another, and the answer kind of unfolds in front of you. Now that's, again, what I've learned, but again, if you, and I'm repeating this for the fourth time probably, but if you want to solve it that way, I have no problem with that at all. Give me a thumbs up if you're with me and just, you know, we're good up till now, Mr. Dion. I think I follow you. Even if you're, you know, 50% of the way with me and you're like, I'm going to need some time to study this on my own, which is totally normal. There is nobody I've ever taught who could come into a chemistry lecture and understand everything just by watching, you know, somebody do it. It's going to take some time for you to practice. Well, you know, here we go with chemical reactions. You know, this was in the title of this is in our title slide, and it took us until almost the end of the lecture to get to it. But let's finish up by talking about chemical reactions and equations. So a chemical reaction is a process in which one or more substances is changed into one or more new substances is a chemical reaction, right? In a chemical reaction, we're actually having bonds broken, chemical bonds broken, bonds formed. We're taking substances and we're making new substances. And so a chemical equation uses chemical symbols, right? The elemental symbols to show what's happening during a chemical reaction. On the left-hand side, we put what are called the reactants. Sometimes people will call those the starting materials. I don't have any problem with that. And then on the right-hand side, we have the products. We always call those the products. So reactants and products. And let's say we had a reaction between hydrogen with oxygen to form water. So this is actually, if you're really astute, if you've been reading ahead or studying ahead, which I don't have any problem with, you might know that this is the reaction that represents the combustion of hydrogen. If you've ever heard of the Hindenburg, so the Hindenburg was an airship that was filled with hydrogen gas. It blew up in Lakehurst, New Jersey in the 1930s, I guess. It's also on the cover of Led Zeppelin 1, I think. Anyhow, I'm just talking about combining hydrogen and oxygen. Let me write it up here a little bit bigger. If we take hydrogen and we combine it with oxygen, we can make water. Now, if you've studied chemistry at all, your head's hurting by looking at this equation because it's not balanced, but I'll get to that in a second, okay? So here's some ways of representing it. Let's say for a hydrogen atom, we represented it as these little gray balls like this. And for an oxygen, sorry, not a hydrogen atom, a hydrogen molecule, we represented it as these little gray spheres attached. And for an oxygen, we represented it as these red spheres attached. Our water molecule is this thing here. So what happens when we combine hydrogen and oxygen is that we actually get two hydrogens, right? We have two of them here, combining with one oxygen to give you two molecules of water like that. Now here are the three representations right here. Let me expand this a little bit. Okay. Now we could say, okay, great. If we take two molecules of H2, combine it with one molecule of O2, we get two molecules of H2O. Good. Another way you could represent it, or another way you could describe it, is you could say, instead of just having two molecules, what if you had 2 moles, right? If you had 2 moles of hydrogen, it would combine with 1 mole of oxygen to give you 2 moles of water. Well, how much does 2 moles of H2 weigh? Well, 1 molecule of H2 weighs 2.02 grams. So if I take 2 of those, I get 4.04 grams of hydrogen. So I take 4.04 grams of hydrogen, I combine it with the mass of 1 mole of O2, which is 32 grams. Now look, if you tally these up, you get 36.04 grams. And look at this beautiful, beautiful stuff over here. Remember I asked you to calculate the molar mass of water in your head earlier on? And we got it eventually. It was 18 grams per mole. So look, if I form 2 water molecules, the total is 36.04 grams of water. Look familiar? Absolutely, right? The mass of water that's formed is the exact same amount of mass that I put in, right? The amount that you put in is the amount you're going to get out in chemistry. Okay, we are not going to create matter and we're not going to destroy matter. That's the law of conservation of mass. Now that's a good thing because you're going to take advantage of that law even when you're not even thinking about it, to solve problems that involve masses and balanced equations. All right, so how to read chemical equations. I mean, this is just kind of a helper here for people. Let's say you have this reaction. It's a really simple reaction. Does anybody here ever burned magnesium before? This represents the combustion of magnesium, of Mg. Has anybody ever done this reaction? You can, if you buy a piece of magnesium, you can do it. Done sodium and thermite. Well, not that. Okay, just taking some magnesium. So magnesium is just a metal. If you take some magnesium and you burn it, in the presence of a blowtorch or something, or just a propane torch, or a Bunsen burner, just a flame, it will ignite, and it burns with a really bright flame, and it forms an ionic compound, doesn't it? It forms magnesium oxide. Well, the ways that we could read this, or we could say 2 atoms of magnesium combined with 1 molecule of oxygen to make 2 formula units of magnesium oxide. Remember, these words have meaning, right? An atom of magnesium, because it's just a single atom. Remember, oxygen is one of the diatomic elements. What are the diatomic elements? Have no fear of ice cold beer, right? Have no fear of ice cold beer. Okay? H2, N2, F2, O2, I2, Cl2, Br2. American students seem to like the whole Brinkelhoff thing. That's fine. Okay? Anyhow, that works, whatever. And we make 2 formula units. Why is it called a formula unit and not a molecule? Because magnesium oxide is ionic, isn't it? Okay, it's comprised of magnesium, a metal, and oxygen, a nonmetal. Another way we could read it is we could say, okay, well, 2 moles of magnesium combined with 1 mole of O2 to make 2 moles of magnesium oxide. Or if we wanted to break it down in terms of masses, we could say, well, if I look at magnesium on the periodic table, if I have 2 moles of magnesium, that would give me 48.6 grams of magnesium. It's going to combine with 32 grams of oxygen, and it's going to make 80.6 grams of magnesium oxide, right? That's the mass of 2 times the molar mass of magnesium oxide. Anyhow, same thing over and over. Look, I hope that nobody would think this by now, because I feel like I've harped a lot on this tonight, but you would never, ever, ever, ever do this. The stoichiometric coefficients in a balanced equation, the 2, the 1, the 2, they have nothing to do with mass. It's not 2 grams plus 1 gram gives you 2 grams. Why can't you do that? The reason why you can't do that is because magnesium, oxygen, and MgO all have different masses. Okay? All right. There we go. Well, let's move on from there and talk about balancing chemical equations. It's not just a, you know, what's the word I was looking for? It's not just trial and error. Sometimes it can be, I guess, if it's a really difficult problem. But balancing equations here, I mean, this is the path that's laid out in our textbook. It says, write the correct formula for the reactants and products on the left side and the right side. Okay, so let's do this reaction here. I'm going to help you with it, right? We're learning chemistry, so I'm going to help you. It says ethane reacts with oxygen to form carbon dioxide and water. So ethane, you might not know the formula of ethane, but it's C2H6. It's a gas at room temperature. It combines with oxygen. Oxygen is O2 gas, and it forms carbon dioxide, which is a gas, plus water. Now, if you write water in the liquid phase, that's fine, but this is a combustion reaction, so it's probably producing steam. So we'll put gas like that. Now it says in the second step, it says change the numbers in front of the formulas, which are the coefficients, right? The coefficients of all these right now is 1. But it says to change those coefficients to make the number of atoms of each element the same on both sides of the equation. You cannot change subscripts. You can't change any of these subscripts here. If you do that, you're in trouble. Okay? You cannot do that. That's illegal. And here's my trick. Okay? Obviously, the last step is check, but here's my ace up the sleeve. My students sometimes ask me, Mr. Dion, do you have any tricks? Here's the best trick you'll learn when it comes to balancing equations. You ready? Whenever you have an element or a molecule on its own with just one atom, right? O2 is just oxygen. You save that for last. If you leave that for last, you can do whatever the hell you want with that. You can put any number you want in there. So that's kind of like the ace up your sleeve. Let me show you what I mean. Watch carefully. We have 2 carbons over here, but we only have 1. So that means in front of my CO2, I'm going to put a 2. So now I have 2 carbons here and I have 2 carbons here. Carbon's balanced. Let's move on to hydrogen. I have 6 hydrogens here, but I only have 2 over here. What times 2 is going to give me 6? Well, the answer is 2 times 3 is going to give me 6. And so I'm going to put a 3 over here. So now my hydrogens are balanced and my carbons are balanced. Now let's look at the oxygens. Over here, I only have 2 oxygens. Could anybody answer me, how many total oxygens do I have on the product side? Total. Total number of oxygens on the product side. The answer is 7, right? I have, let's look, I have 2 times 2, which is 4, plus 3, which gives me a total of 7. So that means, again, on the product side, I have 7 oxygens. Now over here, I have 2. Something, we'll call it x. X times 2 equals 7. What does x equal? 7 over 2, right? Which is 3.5. Oops, I didn't want to put that. I wanted to put 7 over 2, like that. Now my equation is perfectly balanced. Every element is balanced in this equation. However, something I've learned since moving to America is we never leave fractions in a balanced equation. Now in Canada, it's not uncommon to do that, but in order to eliminate that fraction, we'll multiply everything by 2, and we'll get this equation. 2C2H6 plus 7O2. You guys remember 702? Where my girl's at from the front to back? Is you feeling that? Put both hands up. Can you repeat that? Try to take my man's. Anyhow, so there we go. There's a perfectly balanced equation. All right. And that's how you balance an equation. All right.